Time for some astrophysics. What we're going to do today is to use Python to validate Kepler's three laws of planetary motion. So I think it's important to realize that Kepler didn't know Newton's second law. Kepler didn't know universal gravity. He didn't know any of that stuff. All he did was figure out very useful ways to plot the positions of planets with respect to the sun over the course of many time frames. And so with that, he had these three laws based on the data that he collected. Number one, the planetary motion is the shape of an ellipse, with the foci being the star, the sun. Number two, as the planet moves around, and you kind of like calculate the area that it swept out in a certain amount of time, anywhere in the orbit it's going to sweep out the same area, so equal areas and equal times. That's kind of a weird one, but that's what he got. And then three, the orbital period squared is proportional to the semi-major axis of that ellipse. So we're going to do this in Python. And so the first thing we're going to do is start off with our sun right here at the origin, and our planet some distance r away with an initial velocity v0 like that. Now, Kepler did not know the mass of the sun. Kepler did not know the gravitational constant. He didn't know the size of the solar system. So he didn't know those units. So we're not going to use units either. Just to kind of like say, hey, we understand what you're going through. So I'm going to give this a value, the mass 1, radius 1, velocity 1, mass 1. We're just going to use simple units, which would be nice. Okay. We're just trying to prove these things. We're not trying to show real stuff. Now what I can do, and Kepler did not know this, I can calculate this vector r, the position of the planet, and I can calculate the momentum, which is a vector p of the planet. Now I can calculate the force, F, negative g, mass of the star, mass of the planet, over r squared, r hat. So, Kepler didn't know that, but we know that. And we can model the motion of this as 1 over r squared type of force. And that force, if I break my motion into short time intervals, which is what I always do, you've seen that, then I can assume this force is constant in both magnitude and direction, and I can set that equal to the rate of change of momentum. So if I do that, I can write the following. I'm skipping some steps because we've done this before. So if P1 is the momentum at the beginning of that time interval and P2 is the end, I calculate the force, I multiply by my time step, I add it to P1, I get my momentum at the end. All right, so now maybe it's over here, and that's P2, and that's P1. Okay. And so that makes the assumption that my force is constant, but if my time interval is short in time, then it's fine. Next, I'm going to assume that it has a constant momentum during that time interval, which I just changed, and I can say the following: P is delta R over delta T, which is R is the change in position, and that's the velocity times the mass. So from that, I can solve for the position doing the same thing. R2, R1 plus P over M delta T. So I calculate the force, I use that to update the momentum, I use that to update the position, and then I just do the whole thing over and over and over again. Okay, let's go ahead and build this model. I'm not going to make a 3D model. I'm only going to plot it as a graph just to make things simpler. So let's just get started and make this code, and then we'll go ahead and use that to check that it is an ellipse. Okay. Python activated on. So here we have, I'm using WebVPython just because it does better graphing. I'm going to make that bigger, scroll up, maybe one bigger. Okay, I print one just to run it one time. Let's just put our constants, g equals 1, m equals 1, m equals 1, r equals 1. Okay, now we do have a thing here with the initial velocity, because if you have your velocity too small, it's going to like get too close to the sun and we'll have a calculation error. If you make your velocity too large, it's going to escape. So let's just start with v0 equals 1. That one does work. Okay. Now I'm going to put my my sun at the origin. So I'm going to actually make two graphs. So let's make, two curves. So graph G1 equals graph. We're going to plot a trajectory. So x tidal equals x, y tidal equals y, and then I'm going to put the width 400. Oops, what the heck did I do? I've been having problems typing with my computer lately. So x tidal equals x, y tidal equals y, and then width equals 400, height equals 400. Now I'm going to make two graphs. The first one's going to be the trajectory of the planet. I'm going to call it F1, G curve, color equals color.blue, and then dot equals true. So when I do dot equals true, when it plots the thing, it's going to show you the current location of the plot, which is kind of cool and would be very useful. And now the sun is going to be F2, G curve, color equals color dot red dot equals true. And now you may be thinking, hey, the sun's not going to move. Why are you making a graph? Because I want to show where it is. So I'm going to go ahead and put that there, F2 dot plot 0, 0. So my sun is at the origin. Let's just go ahead and run this just so I can show you that it is indeed there. And I'm going to save it because I've been having typing errors lately. So there's my plot, right? I don't have the planet yet. Okay. Now I can have the planet. So let's give this r start equals vector r0, 0. And then p is going to be equal to m times vector 0, v0, 0. So I'm moving in the y direction, right? I'm starting it with at a location where I can control things. You could give it an initial velocity in any direction, but if I know this, it's going to be easier to draw my ellipse. That's why I'm doing that. Okay. Oops. Now I need t equals 0. And my time step, I'm going to use a time step of 0.001. dt equals 0.001, just because I know that it'll work. Okay. I got G, I got that. Okay, let's go ahead and, yeah, I'm going to do that. And let's just do R equals R vector 0, 0, 0, R 0, 0. And this is kind of weird, actually, I'm thinking ahead. I'm going to use that for something else. So let's not worry about the R start right now. Let's just make a loop. While t is less than 5, rate 1,000. So I'm going to count until time is 5. Again, the units don't really matter here. And I'm going to say don't do more than 1,000 calculations per second, so it will run in real time. The first thing I want to do is to calculate the force. F equals negative g times m times norm r. So r is my vector position, and norm r is a unit vector in that direction. Built into WebVPython, I don't need to do anything with that. Divided by mag r squared. So there's my force. Now I'm going to update the momentum. P equals p plus f times et. Now I'm going to update the position. R equals r plus p times et divided by m. And now I'm going to plot it. F1.plot. So I want to plot x versus y. So that's the rx.x is the x component of the position. R.y is the y component. Now, if you don't increase your value of time, the loop will run forever. I think this should work. Let's save it again, because I've been very careless lately. And let's run this. So there you go. Okay, so this is actually a circular orbit. If you'll notice, so I have the origin right here at 0, 0. And over here, this is at -1. Up here, down here, that's at -1. So this is it's a circular orbit. It does not look circular because my scales aren't quite set the right, and that's fine. That's fine. Okay. So let's make it a non-circular orbit and run it for a little bit longer just so we can see what's going on. So I'm going to, let's try increasing the speed. And again, you should calculate the escape velocity and make this less than the escape velocity. But if I do 1.2, that should be okay for the initial velocity. And my graph's a little bit. Oh, I got to run it for a longer time. So let's run this for 15 seconds. And I'm going to just change this even though it's not the right shape, just so the graph fits better in my super zoomed in thing. So there's the sun, right? And it's one of the foci, the other one would be over here. We're going to get these values, okay? But we have the thing working. It makes it, oh, I just happen to make a complete orbit. Nice. So now, how do we show that this is indeed an ellipse? Well, let's jump to the board for a second and talk about the mathematical function for an ellipse. So I can erase everything. Suppose I have an ellipse centered at the origin. So I have two foci here and here, and I can draw it like this. So this is my semi-major axis. We're going to call that B. This is my major axis. We'll call A. And so the coordinates here follow x squared over a squared plus y squared over b squared equals 1. Is that right? Yeah. And so I need to find A and B. So the first thing I need to do is to find A and B. And so I'm going to do that in kind of a simplistic way, right? Because I'm going to just use my graph. I don't want to do the best way. And we'll find a better way later, okay? But what I could do is I could just look at the graph and find the distance from here to here, and that's B over 2. And then I could find the distance from here to there, and that's 2A, 2B. Or is that not 2B? That's the question. I mean, if you can't include some Shakespeare jokes in your physics, then you're not trying hard enough, right? So I'm going to go back, and I want to I'm trying to decide, should I just go ahead and measure those? Let's just go ahead and talk about how we're going to plot that. So then we'll just do Python all at once. So I can get that from my graph. Next, what I want to do is to make a new graph to plot. And how do I plot this? What I can do is to have different values of x and find the values of y. So let's solve this for x. So I have x squared over a squared equals 1 minus y squared over b squared. Now I'm going to multiply both sides by a, and I get, and take the square root. No, I want to solve for y. Let's solve for y. So I have y squared over b squared equals 1 minus x squared over a squared. Now I can multiply by b, take the square root and multiply by b, and I get y is b times the square root of 1 minus x squared over a squared. So if I know my x value, I can calculate my y value, but I can't, right? Because I actually get two values here. I'm going to get a positive value and a negative value. So I'm actually going to do that twice. I'm going to say y plus, and then I'm going to say y minus is negative b square root of 1 minus x squared over a squared. Then I can just take my x value right here. I'm going to start with some x value. I'm going to move it this way. And for each value, I'm going to calculate y plus, y minus, y plus, y minus, y plus, and then I'm going to plot it all out. So that's what I'm going to do. So I need to find b, I need to find a, and then I need to get this graph. Now, I will have a problem because my graph is not centered on the origin. I have the sun at the origin. We'll fix that in just a second. Okay. So back over here to Python. Oh, I want to stay right here. Okay, so right here, this is centered, right? I actually can find my origin because I can just look at, there's two ways you could do it. But I can look right here. I should write this down. I'm going to write it on the board. Okay, so for B, it's going to be equal to 1.61. And this is just an approximation. You can do this better. Minus, that's going to be, it's going to be 1.61 minus negative 1.61 divided by 2, so 1.61. So that is my value of B. Because if you go down here, oh, I didn't even switch to computer. There, sorry. So here's my value of B. right there. 1.61, and then negative 1.61. Now for A, I'm over here. This is at 1, right? I set that equal to 1. So A is going to be equal to 1 minus the distance over here, which I get as negative 2.57. So this is going to be plus 2.57, and then I divide that by 2. And that's my value of A. Okay, so now I have A and my B, so I can go ahead and plot this thing. So let's do this. Up here, I'm going to make a new function, F3 equals G curve, color equals color dot green. Down here, I'm going to go ahead and write my A and B values. So A is going to be equal to 3.57 divided by 2. B is equal to 1.61. And those are just approximate, but that's fine. Now, after I run the whole curve, then I'm going to plot it. So I'm going to start off with x equals, it's going to be shifted. It's going to be off. Okay, let's start with x equals A. dx equals 0.0, let's just do 0.01. And then I want to move my x value until I get to negative A. And I'm thinking right now I actually need two curves, because if I plot the y plus and the y minus at the same time, it's going to go up and down like that. So I actually need two functions, and I'll come back and make that. So while x is greater than A, and I'm going to put right here x equals x minus dx. That's going to move it over there. Up here, let's make a second curve, F4, G curve, color equals color dot green. So I'm going to be drawing these two at the same time. Down here, now, so once I have my x value, actually, I'm going to start right here. I'm going to calculate y plus as b times the square root of 1 minus x squared divided by a squared. Y minus is going to be minus is equal to negative b times the square root of 1 minus x squared divided by a squared. And now I'm going to plot those two. So F3 dot plot is going to be x yp. F4 dot plot is going to be x ym. And now it's not going to work, but it kind of works. Should. So it's going to orbit and then it'll plot. So we got to wait. Sorry. I should have taken off the rate statement. But this gives us time to spend time together, right? It's not just running a calculation, it's time well spent. And then it didn't do it. Unless it's, why didn't it work? While x is greater than a, negative a. That's why. While x is, yeah. Okay, now I turned off the rate statement so we don't get to spend time with each other. There. So there's my ellipse. And I'm not going to do it, but it's pretty easy to see that if I shifted this over by the amount from the sun to here, right, the actual center, then those two ellipses would be the same. I mean, if you want me to do it, I can. This is the value, negative 4, negative 5.11. So if I just take my x values, and when I plot it, minus 0.511, minus 0.511, let's just see what happens. The goal was just to get it to show that they're the same thing. Oh, I messed up a little bit. Okay, well, you see it is the same. I think we're fine. Kepler number 1, check. Okay. Now, Kepler's law number 2 is a little tricky, right? Because how do I calculate equal areas and equal times? First of all, I want to have my, what did I use for my velocity? My velocity was 1.2. Let's do 0.7. There, okay. So my ellipse is wrong now, so I'm just going to delete that because we're done with that. We're done with the first law. Sorry if you wanted to save that. I didn't save it, but we have our thing working again. So how do I calculate the area of a curve, of a sweep, right? So let's go back to the board up here and figure out how to do that. That's not right. That's right. Okay. So here's my sun, and then here's my object moving like that. And let's say it goes from here. We want to show this, right? Equal areas, equal times. So over here, in the same amount of time, it doesn't move as far. So this area is the same as that area. Well, what if I use a super short time? So in a super short time, I have this is the motion it moved. So it's actually more like a triangle. So let's just zoom in, and I can say here it looks like this. So this is v dt. That's how far it moved. That's r, and that makes this trapezoid, right? If I know the length of this and the length of that, and they're as vectors, I actually can calculate the area as area, the magnitude of r cross v dt. So we can use the cross product. But that's not the area I want. I actually want this area. Oh, 1/2. So I can take each time interval and calculate the area for each time interval, because it is a trapezoid. It's a part of a diagonal of a trapezoid. And then just plot dA. I'll actually call this dA, right? That's the area for each step. And so I don't have to do 2 time sweeps. I can just do a bunch and plot them all, and they should all be about the same. So that's what I'm going to do. Not the best way to do it, right? But again, the problem is, how would you calculate the area of that? There are ways to do it numerically. You could just add, if I wanted to start here and end there, I could just add up all those dAs, and that would get the total area. And then I could do it over here again. But it's a little, I want to do this because I want to have a video that lasts under 80 minutes. So that's why I'm going to do it this way. Okay, let's go back to the computer. I'm going to make a new graph down here. So I'm going to put it below this one. I'm going to call it G1 equals graph G2. Why can't you see that? Okay, that's better. G2 equals graph. And let's just put the labels. X title is going to be time, and then Y title is going to be equal to dA. Width 400, height 200. And then the graph, I'm going to call that F5 equals G curve, color equals color.blue. My default color is blue. You have your own default color, and that's fine. So in my loop, I want to calculate that area each time. So I have my R vector, I have my P vector, right? So R cross P is dA, but then I have to divide by the M, and I have to divide by 2. So I can do that all in one fell swoop. dA is going to be equal to 1 divided by 2 times M. And then times, of course, you don't even have to do that because we're just showing that it's constant, times the cross product of RP, magnitude. And then I'm going to plot that. So I called that F5. F5 dot plot T dA. Let's run it. There's that, and there's that. And that does not look constant, but that is totally constant, right? So we have some small rounding errors here, but you'll notice that this goes from a value of 0.35 to a value of 0.35. But then it just scales it because nothing changed. You could fix this if you wanted to, but I don't think we need to. We have shown that dA is constant around that whole thing, so any areas that you sweep through would also be constant. Second law, check. Okay, now for the third law. Do I need to draw this out? Okay, so what I need to do is to make a program where I let it orbit one complete orbit. And the time for one complete orbit is t, the period. And then I need to measure b, right? I don't need the major axis, I just need the semi-major axis. And because of one important thing. Let's just sketch this out just to make sure that we're all on the same page. So because I have an ellipse like this, there's my sun, there's my other thing, so it goes like this. Because I start on the x-axis with the velocity in the y direction, this highest point up here is b, right? So b is equal to y max. So that's important. So as I move this around, I can just find the largest value of y, and that's my b. Okay. Now what about the period? How do I make it run exactly one orbit? You could just take that program and run it and adjust the final time until you get over here and it stops and record that. That's fine. Okay. But what I'm going to do is to use this r start, and then I'm going to let the object move around here. Then here's my value of r. So this is going to be the difference between r start and r, and when that gets super small, then I'm going to stop it. But you have to be careful because it starts super small. So what I'm going to do is to say if it's orbiting if this is greater than some value and it's after some initial time. So I need to get it far enough away, right? So after 1 second. I'm going to assume I can't have an orbit less than 1 second. And then so then I'll just say, okay, until it gets back to that point. And then I'll just say what's the time. It's not going to be perfect, but it's going to be good enough. Okay. Let's just start a new program because I am going to save this because we want to make a new program. So I'm going to just copy this, edit the code, copy the whole thing. Oops, hey, that was bad. Copy the whole thing, and then I'm going to make a new code, new trinket, WebVPython, Python. And then I'm going to delete that and paste it. And then I'm going to run it just so that it runs. And then I'm going to go up here and save it, Kepler 3 function. So what I want to do, I don't want to plot the trajectory because I don't really care about that. Instead, I'm going to make this whole thing as a function. So let's just get rid of the things that we don't need yet. I'm going to get rid of these curves because they're just kind of messy. And P, that's fine. R is fine. I don't need these. Don't need the rate. F, P, R, I don't need DA. I don't need the plot. And let's go up here and define all of this as a function. I don't need V0. Then let's call this R0. I don't need that either, but I'm going to put R0. So up here, I'm going to say def T orbit. I don't know why I'm calling it T orbit. And that's going to be the time that it takes to orbit. And I want to give it two parameters, right? I'm going to use my masses are all the same, but I want to be able to give it an initial velocity and an initial position. So let's say R0 and V0. Those are my two starting parameters. And then all of this stuff is going to be part of my function, so I need to indent that. So I'm going to have G, I'm going to have all this stuff right there. My R start is going to be equal to, this should be R0. And then P is going to be, that's V0, that's fine. That's fine. Now this is, I'm going to change that. That's fine, that's fine, that's fine. So that looks all fine. So I want to just say, how do I know if it's one orbit? So let's make this thing up here called orbit equals true. This means it's in an orbit. So instead I'm going to say while orbit. Now you got to be careful here because you can make things run forever. So while it's in orbit, I'm going to keep doing the following things. Now how do I know if it's not in an orbit? So down here, I'll just put right here, if t greater than 1 and, let's calculate this r. So r diff is going to be r minus r start. If mag r diff is less than, I'm going to pick a value, let's say 0. I don't want to go too small. I think that might work. Because if you get too small, you could jump over your point and it will never end. Let's just do 0.1. I'm scared. Okay. Then it will run, and when it finishes, though, if that's true, then orbit equals false. So it'll stop, right? And then once it stops, then I want to return, I'm just going to return the time for it now. So let's return t. So let's just try this. Print t orbit. I'm going to give it a position of 1 and a radius of a velocity of 1, just for fun. Let's just see if it works. If it doesn't work, I'm going to be kind of embarrassed. Okay, it worked. I think that worked. Let's try decreasing this to 0.01. I'm scared, but I think it should work. It worked. Okay, good. Whew. So I have the time. Now I also need to return my, my b value. So in here, let's also say b max, or y max, I called it y max. Y max is equal to 0. And so then as it orbits, I also want to check if r dot y is greater than y max, then y max equals r dot y. Right? So that just says if my y value is greater than what I already have, then set that to the max. And now I'm going to return both of those things. I'm going to return t and y max. So let's just do the same thing, right? So, but now I should get two things outputted. So there you go. Why? It should be a circular orbit, right? And so I get, because I had 1 and 1. And so it does look like it's working. So I think I'm pretty happy. Now we can make a graph. So G1 equals graph. Let's just do x title. I'm going to plot t squared versus b cubed. That was it was, right? It's t squared, yeah, t squared versus b cubed. So title, x title equals t squared. No, I'm going to put b squared, b cubed. B cubed y title equals t squared. And then width equals 400, height equals 200. And then I need a curve to plot. F1 equals G curve, color equals color dot blue. And so again, I'm gonna do this a whole bunch of times. I'm gonna use different values of V, a starting V from, let's say, 0.6 to 1.2. And then I'm gonna plug that into my values. I'm gonna get back both a period and a B value, then I can plot those. So down here, that's all part of my loop. I don't need this anymore. So let's just start with our V equals, let's say 0.6. And then dV is 0.1. And then what I'm going to do is to say while V is less than 1.3, and I'm going to have V equals V plus dV. And then I put that in there because I don't want to forget. So the first thing I'm going to do is I'm going to use that value of V. I'm going to plug it into my function. I'm going to get my constants. So I do need those as, there's two of them. So I'm going to say TB equals T orbit. I'm going to pass to it, what was the first one? I passed to it R and then V. So I'm going to use, let's say up here, R is equal to 1. So, oh, I don't want to do that. Let's say R is equal to 1. R, V. So I'm going to pass two of that. It's going to give me two things back. It's going to give me a T and a B. And then I'm going to plot that. F1 dot plot B cubed T squared. Let's see what happens. Straight line. Straight-ish. Right? It's straight-ish. It's not perfect, but it's fairly straight. I'm pretty happy. Okay, so you could get more data points if you wanted to. It's not completely straight because remember, I'm not always making a complete circle. I could fix that if I make my dt a little bit smaller in my loop, in my function. Let's see what happens then. That's still a little crooked. Well, it could be my b max too. But overall, I think I win. I showed Kepler's 3 laws. And I did not make it under 30 minutes, which is kind of surprising. So I will put a link to these two programs down below so that you can play with them. And there we go, the end. Talk to you later.